Hello, in this video we're gonna learn about the concept of counting. Here we're gonna answer the questions such that how many 4-digit number can be there if repetition of a number is allowed or if repetition is not allowed. Or questions such that if a man has 4 suits, 8 shirts, 5 ties, how many outfits can he put together? So let's start with these questions. So for example, if I need to have 4 digits, how many different digits can I have? So for the first slot we can have 10 digits for 0 to 9 and another 0 to 9 and another. So what does it mean? We could have 10 to the power of 4 or 10,000 different digits. And intuitively that's because we have 0, 0, 0, 0 and then 0, 0, 0, 1 all the way to 9999. So 9999 plus another 1, that's 10,000. And if repetition is not allowed, so the same way intuitively we could see that we could pick a 10 digit here, 0 to 9, but 1 is fixed, so what we have left? Only 9 to pick from. Then you fix 1 here, and then what you have left is 8 to pick, and then 7. So basically you have 10 times 9 times 8 times 7, which is 5040 different digits to choose if repetition is not allowed. And for the next question here, you have a man with 4 suits, 8 shirts and 5 ties. He can make 4 times 8 times 5 or 160 outfits. And this is what the concept of counting is about. So let's see here. What we just did last example for the outfit is we call multiplication principles. If there are n possible outcomes for the first event and m possible outcomes for the second event, then there are n times m possible outcomes for the sequence of 2 events. Hence, from the multiplication principle, it follows that for 2 sets A and B, so A times B is the cardinality of A times B is the same for A times cardinality of B. So for example, a child is allowed to choose 1 jelly bean, 2 out of 2 jelly beans, 1 red and 1 black. So we could picture it as a tree diagram. So you could have either red or black jelly bean, first choice, okay? Then the second choice, he can have a gummy bear out of 3 gummy bears. 1, 2, 3. So he may choose black and then have 1, 2, 3. So what do you have here? So the question, how many different sets of candy can the child have? So as you see, 1, 2, 3, 4, 5, 6 of them. Or simple way is we could say he chooses 2 at the beginning and then he will choose 3, which is 2 times 3, which is 6. And this is the multiplication principle. Similarly here, a frozen yogurt shop allows you to choose 1 flavor. So how many we have? 1, 2, 3, 4, 5, okay? And then 1 topping. How many toppings we have? 1, 2, 3. And the condiment, either whipped cream or coconut, so you have 2 of them to choose from. And the question is how many possible desserts are possible? Again, this is a multiplicative property, which is we have 30 different desserts. And of course you could draw this with a tree diagram. The first choice you have 5 and then 3 and then 2. It will be a huge tree, but this is how, if you want to picture it. Let's see this example. A video game is began with making selection of 3 menus. So the first menu is the number of player, which we have 4 selections. So you have 4 selections, or you could draw 4 and a tree. 2, 3, 4. And the second will have 8. So then each one of them will have 8. So 8. And then the third menu will have 6, so each branch will have 1, 2, 3, 4, 5, 6, which or times 6. So in how many configuration can the game be played, that means you have to multiply 4 times 8 times 6, or 192 different configurations. So the next question here, I have a user password to access a computer system consists of 3 letters followed by 2 digits. So the best way is to picture it. Okay, we have 1, 2, 3 letters, assuming we are dealing with the English alphabet, so we have 26, 26 and 26 letters, and then follows by 2 digits. I mean, I need 10, 0 to 9 and another 10. So how many different passwords are possible? So we have 26 to the third times 10 square different password. So 26 to the third times 10 square different password possible. How many 9-digit social security number are possible? And here I'm assuming you could have a social security with all zeros if you want. So the social security has a 9 digit. So assuming we have all zeros, so there is no restriction here. Even though nobody has this social security number, I guess. So here where we have each cell can have 10 and 10 and 10 choices. So here we have 10 to the power of 9 different 9-digit social security number. Let's see another example. Palindrome is a string of characters that reads the same forward and backward. For example, the word kayak. This is palindrome. So reading it this way, you read kayak, or this way, you read kayak. But how many 5-letter English language palindromes are possible? So let's see. So I could choose 26 letters here, another 26 and another 26 choices I have for this first 3. But this A here must be similar to this one here, so I have only one choice, and this K must be the same here, so I have one choice. So here we have 26 to the power of 3 different 5-letter English language palindromes. Let's see another example. In the original basic programming language, an identifier must be either a single letter or a letter followed by a digit. So here is where we have either just a single letter or a single letter followed by a digit. So how many different identifiers are possible? So we could choose 26 letters, or we could choose 26 letters and 10 digits followed by some digit. And I have 10 choices there. So I choose one of 26, or I could choose 26 and 10. So basically I have 26 plus, because OR is always an addition, 26 times 10, which is 26 plus 210, which is 286 different identifiers. Dinner special allow you to select 5 appetizers, 3 salads, 4 entrees, and 3 beverages. So here I have 5 times 3 times 4 times 3. That will give me how many different dinners are there, which is 180 dinners. So it will give me 180 different dinners possible. Let's see one more example here. In one state, automobile license plate must have 2 digits, no leading zeros. So the easy way is to picture it. So what do we have? We have 2 digits and no leading zeros. That means I have 9 to choose from, don't choose the 0, and 10 to choose from for the second digit. Followed by one letter. So one letter will be 26 to choose from. And then followed by 2 or 4 digits. 2, and then follow by 2 to 4 digits. So either we follow by 2 digits Or we do the same and we follow by 3 digits. That means I have 10 for each digit to choose from. Or we have the same, but then I have 4 digits to choose from. As I mentioned earlier, OR is translated to an addition and is a multiplication. So the answer will be 9 times 10 times 26 plus 9 times 10 times 26. So the answer is 9 times 10 to the power of 3 times 26 plus 9 times 10 to the power of 4 times 26 plus 9 times 10 to the power of 6 times 26. So the answer is 25,974,000.